Hello all, welcome to this tutorials in which we will be looking at obtaining the analytical solutions for some of the MLE estimates. In the class, what has sir has done a couple of examples, and then the steps now which are there were left as an exercise for students. In this tutorial, what I will do is I'll fit in those steps and then give you a full-fledged detailed solution. Now, one important resource that you have to keep in mind is that matrix cookbook that sir has set in the uh, class. Okay, so now without any further delay, let's start with the discussion. Examples of MLE estimation. There I'll take the example 1. Example 1 is one-dimensional Gaussian case. Okay, and this was not particularly done in the class. We directly take the multidimensional Gaussian. I'll come to that just to give you an intuitive idea. How does the solution look like? Okay, now we will explicitly take this. Okay, so now in this case, the class conditional x given y is equal to I now will be a square root of 2 pi exp of minus x minus mu I whole square divided by 2 sigma square. Okay, it's one-dimensional x comma mu I comma sigma I, all of them belongs to R. Okay, so a very straightforward and then a simple case. So now this is for one example. Now the first thing is you have to find the log likelihood, and then you have to find the, so the idea is same. Now you have uh, the form of the density, and then what do? You take the log likelihood over you consider all the examples, you take the log likelihood, so and then take the partial derivative with respect to the parameters, equate it to 0 and obtain the values. Okay, so this is a standard recipe that we will be going ahead in this tutorial. Okay, so now consider we have n examples and obtaining the log likelihood now this will be summation j equals 1 to n ln of p of x given for any given class. I'm just considering xj. This will turn out to be summation j is equal to 1 to n minus ln of sigma I minus 0.5 ln of 2 pi minus xj minus mu I divided by 2 sigma I square. There is a square here. Okay, so now if you take the summation inside, this is minus n log I minus 0.5 n ln of 2 pi minus summation j equals 1 to n xj minus mu I whole square divided by 2 sigma I square. Okay, so now this is the log likelihood. Now you have to maximize this log likelihood. So now what is that you are supposed to do? Now you have to take the partial derivative with respect to the parameter and equate it to 0. Okay, so how do we do it? To maximize the log likelihood, we equate the partial derivative to 0. Partial derivative with respect to the parameters. Okay, so now that means that you take, I just represented you take the partial derivative with respect to this. So individual, so how to take this? This is a constant with respect to sigma, so no need to worry. So now this will come out, and this whole thing can be considered as a constant. So now derivative with respect to the sigma I, now it will be 1 over sigma I. So this is lambda I square. Now it will be 1 over lambda I cube. Okay, so you take care of all of them. So and then so it will be minus n divided by sigma I plus 1 over sigma I cube summation j equals 1 to n xj minus mu I whole square. This you equate it to 0. Now when you do so, now how it will be? So now this will be sigma I square equals sigma I square. Okay, now this is the star of this, the optimal value. Okay. Now see, sigma I square is what you are evaluating. Okay. Now this is 1 over n summation j equals 1 to n xj minus mu I whole square. So now this is 1, and then you take the partial derivative with respect to mu I. Now when you do so, what will happen? Now this is independent of mu, this is independent of mu. Now this will go off. So now you have to take it with respect to mu I. Now therefore, what will happen? This is a function of mu I. So it will be 2 times of this, and then you take this. This is minus mu I. Okay, I'll not go into the taking how do you take the derivative. So all of you should be comfortable with that. So that will be 1 over sigma I square summation j equals 1 to n xj minus mu. Okay, this you equate it to 0. So when you do so, mu I star equals 1 over n summation j equals 1 to n xj. Okay, now these are the two parameters that we can easily obtain. Okay, so now this is nothing but the sample average. Now what you are doing, you take the value and then you subtract the mean and then you square it. So now when we go into the multidimensional case, now each xi will be in Rd, and then the covariance matrix that is there will be in Rd cross D. So now this will turn out to be an outer product, right, in that case. Okay. Now we have to see the similarity now. Okay. Now this will turn out to be the outer product, now giving us the matrix. Okay. So, so now let's take the one that we actually want to look at. So this example, I explicitly uh, took it so that we should be able to see the relationship between the unidimensional Gaussian case and then the multidimensional Gaussian case. To understand that specific relation, we took it up. Okay. So now consider the multi-dimensional Gaussian density. Okay, so this case, now how will be my density look like for a given x? It is 1 over square root of 2 pi to the power of d, determinant of the covariance matrix, into exp of minus half x minus mu, I have to mention it like I, mu I transpose inverse okay. So now look at the matching, the dimension matching. So this is a matrix, a square matrix. So otherwise inverse itself is not defined. Okay, so this is a matrix into a vector. Okay, so you get a vector out of this, a vector into a vector of the same size. This is x transpose x, which is nothing but a scalar. So, and then exp of a scalar, this will give you a scalar, and this is a scalar. Finally, we want this to be a scalar, right? Okay. Now whenever we write any matrix equations, always the initial sanity check has to be now whether the dimensions are matching. Okay, that should be the first sanity check whenever we are dealing with matrices. Okay, now here to bring it up, x comma mu I belongs to Rd, and then the sigma which is there is a D cross D matrix, which is the covariance matrix. Okay, so now you have n samples. Now what do? You take the log likelihood of those n samples. Again, the same standard recipe. Now, considering the n samples and taking log likelihood, what it will be now, this is j equals 1 to n ln of given x. So now if you together, this is summation j equals 1 to n ln of 1 over 2 pi to the power of d, determinant of the covariance, the square root of that, into exp of minus half xj minus mu I transpose I inverse. See, you can remove this. If this I is too much of overloading of notations for you, can remove this. This is for any given class I, because we are assuming that class conditional is a Gaussian. So I am representing that it is for that specific class. Okay, I can easily remove that also. and then it holds comfortable. Just for giving that in mind, I'm writing it mu I sigma I, which is there for a specific, which class are you considering? Okay, so now if it is too much of notation, let's remove that. Let's keeping that in mind, so we will just go ahead with that. So now this will be j equals 1 to n minus half ln of e to the power of d minus half xj minus mu whole transpose inverse xj minus mu. Now this is, so now you can take this summation inside, but now 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 the question is, you have a scalar in this case. Okay, this whole thing is a scalar. Now you have to take the partial derivative with respect to mu, which is a vector, and then sigma, which is even a matrix. And this is a trace is also a determinant is also involved in this. Okay, now how do you take care of these things? Okay, so that will be our that is where actually the identities of the matrix cookbook actually comes into picture. Now now need to now need to take the partial derivative with respect to parameters and equating them to 0. Okay, that is what we are supposed to do now. Okay, now taking it for mu is quite simple actually. Okay, now partial derivative with respect to mu. Now, if you take this, now this whole thing is independent of mu, so no issue. So now, so you have this form. Now we know how to take this. Now this is inverse into xj minus mu. Now that is what it will be. So it's quite simple for us to get. Now this is okay. So now please remember, I'm using summation also and then sigma also, so you should not get it confused. Inverse minus mu, you equate it to 0. Okay. So now what you can do, now this is independent of j, you can take it outside, and then this is the inverse, so you can multiply with this and then you get a I over there. Okay, so you can take care of all of them comfortably. Okay, so because of which now finally the mu star now which is there will be 1 over n. Okay, see finally you will get this out and then you take it summation inside. Okay, you get this n mu, you take this n mu outside here. This is I into some summation of vectors. So summation of vectors is a vector. So a matrix into a vector, identity matrix into a vector. Why I'll get an identity matrix? Because you multiply with by sigma. So you will get a vector. Okay, the same vector holds. So now therefore it finally boils down to xj. Okay, now this is a straightforward, simple thing for taking care of mu. It's quite simple to do it for mu. Now the actual what do you call issue lies with how do you take care of the covariance matrix now. Okay, so now So now we need to take the derivative with respect to sigma. So now our log likelihood is our log likelihood has been reduced to, this is summation j equals to 1 to n minus half into ln of 2 pi to the power of d minus half xj minus mu transpose inverse xj minus mu. So now you take the summation inside. Okay, now because of which it will be minus n by 2 into d log 2 pi. Okay, now and then it's 2 minus plus minus n by 2 into this. Okay, and then minus summation j equals to 1 to n half xj minus mu transpose inverse. This is what it turns out to be. Okay, so now it is too much of things, so we will reduce the notations. Now let's take that. I'll represent this inverse of the covariance matrix as this tilde, and then I'll represent this zj is xj minus mu. Okay, so now with this, how will my new and d log 2 pi minus n by 2 the determinant of this minus half to summation j is equal to 1 to n zj transpose. Okay, there is no change in terms of the notations. Okay, so now there is some mistake that I did. Just 1 minute. Okay, no problem. Yeah, I myself got a bit. Okay, so now what is that we need now? Now we need derivatives of the form. You take the derivative with respect to a. This we need, and then derivative with respect to a matrix ln of its. These are the two things that we want to get. Now, this is my log likelihood. I'll take the partial derivative with respect to my matrix that is there, okay, and then equate it to 0. For that, I should be knowing what are the partial derivatives of this. Okay. So now, here comes some of the important identities of the matrix. Okay. I'll not be going ahead and proving these identities. Okay, I'll be just using them. Now, some useful matrix identities. Some useful matrix identities. Now, all of us knows about the trace. Trace of AB equals trace of BA. Okay. Now assuming that the AB, BA multiplications are matrix multiplications are possible. Okay. Now the dimensions I'm taking into consideration. Okay. So now then trace of ABC equals trace of CAB equals trace of BCA. Okay. These are all standard matrix identities. So now if I take the derivative of this trace of A transpose B, it will be B. Okay. So now we all know the trace is a scalar. Z transpose A C can be written as the trace of Z transpose A Z. Correct? Now this I can write it as trace of Z transpose into A. Now we know that this is one, this is same as trace of A into Z transpose. Correct? Now what is the derivative of this? Now derivative of A transpose B. Okay. If you have this, okay, and one more thing. Okay, I forgot. This is derivative of A if you have trace of AB, which is B transpose. Okay, one more identity that is needed for us. So now putting all of this together, therefore, the partial derivative with respect to the matrix A is same as taking the partial derivative with respect to trace of A ZZ transpose, which is ZZ transpose whole transpose. This is Z transpose. This is the outer product of the vectors Z. Okay, so now that means that now going back to this is done. I can individually take care of this. This is done. Now this will give me a Z transpose or ZJ transpose. This is done. This part is done now for me. So now I should take the gradient with respect to this. Okay, that is what is pending for us now. Okay, now let's do that. Now we need the other derivative. Now we need other derivative log of determinant of A. Now let's consider a scalar x. Okay. Now x we have always used for something. Okay. So now if I have there is an identity which like for example let's have some beta belongs to R, it's a scalar. Now if I have beta of ln of this is there, now then it is trace of A inverse okay. Now there is this identity. Now using this identity, now we will go ahead. Now A is a matrix. Now each element Aij which is there can be thought of as a scalar. Now because of which I can write that I can take the partial derivative with respect to this Aij. So this is trace of A inverse A, correct? So now the overall question is, now I have taken with respect to one element of this matrix. So the remaining elements, I have to take it into consideration. Now, what do you mean by this? Now you take the gradient. Now what will happen is, in that position Aij, it will be 1. In every other position, it will be 0. Okay. Whenever I take this gradient, now what will happen is, so now this partial derivative in this case is a matrix with 1 in position I comma j and zeros elsewhere. Okay. Now therefore, now what will happen? This is a matrix. This is a matrix. Now the dimension is taken care by the construction itself. Okay. So now, since this is a matrix multiplication, I can know what is its element. Okay. I can actually know it comfortably. So now A inverse J A, I can know what is the element at KL location. Now it is summation with respect to S inverse KS. Now I am assuming that you are quite comfortable with representing a matrix multiplication using these formulas. Okay. Okay. Now here it's the element in the A inverse matrix. Now this is the element in the what do you call the partial derivative matrix. Okay, there is no such term, but you can think of it. Okay, now this will be 0 if L is not equal to J AKI inverse if L is equal to J. By construction, now I am able to obtain the element. Now I will be able to get the trace very comfortably. Okay. Now getting the trace is not at all a difficult thing. So now trace of A inverse Ij. Now this will be inverse Ij. This Jj. Now this is nothing but Aj inverse. Okay. Now I'm able to get it for one element. Okay. Now if you are able to get it for one element, you have taken with respect to one element. So now you have to take the respect with respect to the whole matrix. Now what it will be, see the important thing to observe is now Aij, now you have actually taken the inverse and then so you have taken the inverse of the transpose. Okay. Now you have taken the transposed element. So for Aij, now you are looking at Ji element and the inverse of this. Okay. So now putting all of this together, okay, now this is for one. Now if you put all of them together, now therefore it will be overall thing. This for one element, like that you take it for everything. This is a inverse transpose. Inverse of the transposed element. Now you got the second one. Now from here, you just put them together and then you get it. Now putting these together, okay, you put all of these together and then what do you do? The next step is take the partial derivative, and equate to 0. Take the partial derivative and equate it to 0. That will be n by 2 inverse is half summation j is equal to 1 to n such j transpose 0. So now what will be the value? Now we know that this is tilde inverse is the covariance matrix that we had. This is 1 over n summation j is equal to 1 to n xj minus mu into xi minus mu transpose. This is the outer product. Now when you took the one-dimensional case, it was the square of the difference between the considered data point and then the mean of it. Okay, now if you go back to the one-dimensional case, but now in the multidimensional case, it has transformed into a outer product now between the data vector and then the mean vector. Okay, this is the overall derivation. So in the next part of this same tutorial, now we will be looking into the generalized discrete random variable version that was discussed in the class, And then we will look into the constrained optimization, how to get the parameters in that case. Thank you.